Hello, this is Jim Corkins, and we're going to continue on with 7.2, and actually part 1 of light. And this is specific to refraction of light. And so that is a term about how light actually bends, and under what circumstances will light actually bend. All right, so if you haven't done your reading, please go to Coletta chapter 23, and also read chapter 24, and that is on lenses. This is going to be for sapling, which is the homework specific to optics, and also lab 13. So refraction of light occurs essentially because a beam of light, an incident ray, a beam of light will bend as it goes from one medium into another medium. So if you've ever, from experience, you put like a pencil or a ruler or even a swimming pool scooper pull into the water, and when you do that, you see it kind of bend. Well, what's happening is the light ray, the incident light ray in air, in the less dense medium, is traveling fast, and then at the interface or the boundary between the air and water, the light ray has to slow down, and when it slows down, it begins to bend. Okay, and it gets to bend, and actually bends towards the normal line. And we talked about how the normal occurs at the point where, and I'm going to mark this document up so I can take notes for you guys. So the incident light ray comes in, it hits the boundary between mediums, which is the interface, and at that point where it hits, you'll notice that this incident ray is larger than the refracted ray, and refraction means goes through, and actually in this case bends. Okay, so what is happening? Okay, well, Snell noticed that that this angle, the incident ray, is traveling at one speed, and the refracted ray is traveling at a different speed. Okay, and so that is what is determining that how far it is bending. And so what he did is he made this index of refraction, which is a ratio from the speed of light in a vacuum to the speed of light in that actual medium. And so this is almost like so this incident. So this is called the index of refraction, and a vacuum of space will have an index of refraction of 1, which is it's got the best incidence of refraction. So if this number starts to lower, so if this speed lowers, it has the, I'm sorry, I said the great, I meant to say it has the lowest index of refraction. So how you get 1 is this: if in a vacuum, the speed of light is 1c, and if the speed of light is also in a vacuum, in this case, it is also 1c, so the index of refraction is actually equal to 1 for a vacuum. Right? And so that's the lowest number it could be. Okay? If the speed of light, VCCUUM, if we are talking about another object, okay, another medium, so you have a speed of light is c, and let's say water is slower. For sure, light in water is slower. That means this velocity is going to go down, right? So that velocity is going to go down. Well, that's going to drive that index of refraction up. So 1, which is, it has no units to it. It's just a 1. It has it unitless. It's a comparison, or it's speed over speed, right? Meters per second divided by meters per second is 1. Anyways, my point is is that the index of refraction, if your speed is really low, your index of refraction is going to be large, right? So in a way, that index of refraction is kind of analogous to the density. It's almost like a density. The index of refraction is kind of like a density here, and instead of using rho, I'll just say density. It's almost like the density of that transparent medium, right? The more dense the transparent medium is, you know, the higher that index of refraction is, okay? So what happens is Snell's law becomes this. It becomes, so what I'm going to do is solve this, and I'm actually going to make a relationship here. So if the velocity is equal to, it'll c over n, and that means n1 is going to be equal to c over v1, right? Actually, v1 is actually going to be equal to c over n1. Well, Snell's law for sine of theta 1 is going to be equal to v1, which is equal to c over n1, divided by sine of theta 2, which is equal to c over n2. C over n2. And so what you finally have out of this, I'm going to erase this for now. Is you have this relationship of sine of theta 1 over sine of theta 2 is equal to n2 over n1, right? And that comes from this relationship of the angle is the same thing as its speed. So in the lab that you're supposed to do, there is a really cool simulation, which we'll do in a second, but I attached the link here at the bottom, okay? And you could actually test out how much light is bending or at what angles for different mediums, different density mediums, okay? And I mean, by the more dense it is, the higher the index of refraction, right? But different mediums have different densities, and they all have to be transparent mediums. This is not for for opaque objects, all right? So what you can see here is that air is almost close to a vacuum, right? A vacuum, again, the vacuum of space is got an n equals to 1. That's a vacuum, right? So, and as you notice, it starts to get more dense, right? Diamond is a very dense optic. So what you have is, as you increase in densities, so does your index of refraction, right? So light will bend a little bit in air, right? It'll slow down a little bit in comparison to the vacuum. But then it hits water and it slows down even more, and ice, and then you've got different things like ethanol, alcohol, things like that. So that index of refraction is analogous to density. And it's not a perfect analogy, right? There's some exceptions, but for the most part, it's basically the density of that substance, right? And so a couple cool things happen when a light ray goes from one medium to another, and let's say this light ray is 590 nanometers, okay, and it goes from a vacuum, right? So it's 590 nanometers in a vacuum, right? And it hits water. Well, the weird thing is the wavelength is actually going to change, right? So it's going to go from 590 nanometers to 443.61 nanometers. So looking back on, this is 7.0, and I think this is the third or fourth slide, and this is about the visible light. Well, 590 nanometers is kind of right here, right? So that's, it kind of looks like it might be orange, mostly maybe yellow, right? But then when it hits water, it's going to go down to 443 nanometers, right? But if you've ever actually been in water and somebody's holding a red pail here, like a red object out of the water, and you're in the water, you could still see it as a red object, right? Well, that's weird that an object, when it goes from one medium to another, is going from yellow to violet range, but we're not seeing the color change. So this is a yellow-ish wavelength, right? This, in a vacuum, this would be yellow, right? But when it hits water, it's kind of violet, almost blue, bluish kind of color, right? So this should be, so what that's saying is if you were holding an object that was yellow in the air, or you're just holding like it maybe a yellow object, it should look violet or blue. Well, that's actually not what happens. A yellow object is not going to look blue when you're underwater, right? It's actually going to look yellow. So this is not true. Objects don't change color when they go from one medium to another. What doesn't change when you go from through different mediums is the frequency, right? So even though the wavelength is changing, the frequency is not, right? So again, since our eyes are responding to so what is carrying that light is a photon, and it's the energy of a photon, that little massless, chargeless particle that moves other particles. It gives kinetic energy to all other particles, particles like electrons and protons. And in order for them to speed up and slow down, they have to absorb photons or they have to eject photons, right? Well, this energy equation is basically saying that frequency is what we're seeing. So the energy of a photon impacting against the back of our eye is actually the frequency of that color, right? And frequency isn't changing when it's going from one medium to another. So that's why color won't change. Even though the wavelength is changing, the color isn't going to change it, and that's because frequency doesn't change from one medium to another. Okay. So, what is changing though? Again. Velocity is equal to wavelength times frequency, right? And so that if that velocity is going to go down, okay, so I'm going to do this. I'm going to put velocity over, well, actually that doesn't matter. I'll put frequency here, or wavelength. If your object is slowing down, well, that's going to lower your wavelength, right? But your frequency has to remain constant. So that's how it's balancing it out. In order for it to slow down, its wavelength has to change, but what's going to not change is the frequency. Okay? So that's why objects don't change color underwater, when you're going actually different mediums. Okay? And so this is an offshoot of what we were talking about a little bit earlier. So we had made that relationship that Snell's law was this: the sine of theta 1 over sine of theta 2 equals v1, the velocity of this first velocity of the incident, and this is the velocity of the refracted ray, right? And since velocity is going to be equal to speed of light over the index of refraction, right? What we found out was that sine of theta 1 over sine of theta 2 is equal to n2 over n1. Well, multiplying both sides by n1 and multiplying both sides by sine of theta 2 is how you get this nice, really well-written, crisp relationship of angle to index of refraction, right? And again, it's velocity that is changing, right? And this is, again, the speed of light, and this is the index of refraction, right? It's almost like the density of that medium, of that transparent medium. Anyways, you go into this, and you get this nice equation, right? And this is extremely accurate. 99.99999% of the time, this will predict how much that light is bending, right? 100% of the time. So light is coming in from a less dense medium, okay, to a more dense medium, right? This medium here is a greater medium, is a more dense medium than the initial medium up here. So when light's coming in, it's going to slow down and it's going to bend towards that normal. The more it slows, the more it deviates from its original course and bends towards that normal, right? If it slowed down even more, it would bend even more towards that normal, right? So if you have a highly dense medium, it could be, in some cases, it might look like it's almost coming in on top of that normal, right? So really cool prediction equation, the Snell's law, right? The inverse of this is true as well, right? So if you have light, have an incident ray coming in from a highly dense medium to a lower dense medium, right? Well, that light ray is going to come in, and then it's going to start to speed up. Well, now it's speeding up, and it's going to be bending away from that normal. And the more it speeds up, the more it bends away from that normal, right? So, so you have this angle. So you have a relationship of angles that it bends to index of refraction. Okay, and we could see this in the simulation. So I'm going to pull up the simulation, give you just a little bit of an introduction into what you're going to do. So again, you hit the play button, and this is this particular simulation is in HTML5, so it should work on everything. And you're going to hit introduction, right? So here you have a laser beam, and again, this is not a light source that throws out light in all directions. This is just a laser, so it sends out one beam. So you hit the button to turn it on, right? And you can angle this. And right now, this is supposed to be air. This material is air, which has an index of refraction of 1, and it's listed right here. Water has an index of refraction of 1.33. Actually, this is actually 1.0003. So pretty close to 1. Not exactly 1, but pretty close to 1 is air. Water, much more dense, 1.33. Okay. You have a little protractor that you could measure the angle with over here. So you can see that angle is about, see, that's 10 to, so it's about 36, 37 degrees. And this other angle down here looks like it's about, that's 40, 50, and it's bent to about 50 degrees. The cool thing is, too, you have another tool that you could see the actual intensity of this, right? So it's 100% intensity here. And then a cool thing is some of the light you're seeing is actually reflecting off the surface, which is what would actually happen. And so what this is showing that 91% of the light is refracting through, and a little bit of almost 9% is reflecting off the surface. So you should see, if you're sitting over here and this actually is your eye, you would see a dim light source reflected off the surface. And you would probably see it down here, right? Because our brains interpret things along straight lines. So you would see it right here. Okay? So this is a really cool thing for you to use. It's cool, and you could take data and you could change the medium. You could change it to a custom medium, or you could actually just slide it to glass. You could actually choose glass, right? And notice they kind of show it getting darker, so it's really well set up. So now you can see glass is actually getting less refraction, less of that original 100% is going through, right? So it's cool. You can see the amount of light getting through is actually decreasing the more dense it is, and that means more light is being reflected off the surface. So this is a really cool tool for you to use, and I really like this. Another thing too is the other tools. If you go over here and you turn it on, and we're going to choose water just to be consistent with what we were doing before. I think you could just choose angles right here, and it'll actually show you the exact angle. Okay. And I think we also have a speedometer too. So it shows you right here, since air is pretty close to a vacuum as far as its index of refraction, its speed is about 1, pretty close to 1. In water, it's going to slow down a lot. It's only 75% of the speed of light. So and that's in the more tools area. So here I'm in the intro, you have prisms, and then you have more tools here. So in the more tools area, you could actually get the exact angle and actually see the speed. Okay. So back to our PowerPoint, our PDF rather. So moving on, there are some problems where you go from one medium to another medium and then to another medium, right? And so what you have to do is you have to trace the lines, right? You have the incident light ray coming in. Where it hits that interface, you're going to draw a normal, which is perpendicular to that interface. The interface is going to be horizontal. The normal is going to be vertical, and it's a 90-degree angle. And then it's going to, glass is more dense than air, so it's going to bend towards the normal. It's not going to continue along its straight line, which is this dotted line. It's going to bend towards normal because it's slowing down, and it slows down. And now, when it gets to here, it's going to hit another interface for air, and now it's going to bend back to its original angle, right? And so what you find out, if theta 1 is equal to theta 4, right? This angle right here is equal to this angle here. That has to be because n1 is equal to n4, right? And that if theta 2 is equal to theta 3, which it should be, right? Then that means n2 is equal to n2. So that's kind of silly, but that means the index of refraction is the same. And what that also says is the velocity in air over here is equal to the velocity of what is over here. And that means the velocity in water is equal to the velocity in water too. So pretty cool. So you can make these really neat relationships when something is crossing multiple mediums, right? And again, how much is being refracted, meaning deviating from its original path, is actually covered. Is actually going to be equal to that distance, right? So that deviation distance is how much is being refracted. So the tactic that you tend to do is you're going to draw ray diagrams. You're going to represent the incidence ray, and then when at where the incidence ray hits the boundary or the interface, you're going to draw a normal to that boundary. It should be perpendicular to that boundary, okay? And then if the medium is more dense, the ray is going to be bending, or actually if there is a change in density, the ray is going to be bending, okay? If it's a larger angle, that means it's got a smaller index of refraction. If it's a smaller angle, it's going to have a larger index of refraction, right? And then you want to make sure you label everything. You're going to label your angles, incidence, and refracted, okay? And also you're going to I would also put an I to show the incidence ray and an R to show the refracted ray. But it doesn't really matter, because if you reverse the arrows on those rays, that just actually traces the same path it would take if it was leaving too, right? And so once you have that drawn, then you apply Snell's law. And Snell's law, again, is N1 sine of theta 1, N2 is equal to N2 sine of theta 2. Okay? So here is a cool problem where you have a light ray coming in, okay, and it actually shows what happens. What happens if you have an index, if you have an interface that is vertical, and you have a light ray coming in along that normal, right? Well, it's just going to continue straight through, right? It's going to slow down for sure, but since it's coming in along that normal, it's not going to bend. So that's what you're seeing right here. You have a laser beam coming in along that normal. Here is the interface between mediums, and the normal would just be right here, right? Well, if it's coming in along that normal, it's still going to slow down from through that change from less dense medium to the more dense medium, but it can't bend any more than it already is towards that normal. So it's just going to keep moving in, right? And so now it's slowed down, and now it's in here. When it gets to this part, now if you notice, the normal is bent, okay? That normal is going to be bent. And now it's leaving at that angle, right? To that normal. So that angle that is leaving is going to be right there. So what they're saying is, now you have to draw that normal, right? Okay, so when it's coming in, it's the normal is going to be a perpendicular to the surface, right? And so that light ray is going to be coming in perpendicular to that surface. So that light ray is coming in at a 60 degrees to there that they're showing right there. But you have also this 30-degree angle that it is deviated from, and this is the incident ray, is deviated from that original angle. Okay, so it's coming in, and then when it starts to leave, right here, it's leaving at a 22 degrees off of this line right here. Well, this angle right here, so the angle to what we need really is, since the refracted angle's here and we've drawn our normal right here, this is the index, that is theta sub r, correct? So let's look at this. This is a bit of a geometry problem because we need this entire angle right here. And we know this angle right here is 22.6. So how do we know what this whole angle here? Well, if you look at this normal, which is perpendicular to this point right here, which is perpendicular to the surface, actually makes a concentric triangle right here. And this will be 90 degrees, okay? So this angle right here is this triangle just kind of flipped, sort of. This will be the 60-degree angle, and this is 90 degrees. That means this has to be 30 degrees. So that means this whole angle right here is going to be, so to get the refracted angle, that is going to be that 30-degree angle plus that angle that we were given, which is 22.6 degrees. So that's going to be a total of 52.6 degrees as that refracted angle. The angle that is coming in along on this surface is going to make, here's your 90 degrees, so the incident one, the incident angle, is going to be this 30-degree angle that it was coming in on, okay, that I think we were given. Actually, no, it was coming in at this angle right here, which is just the same triangle, and we're given this is 60 degrees, is this is going to be 60 degrees, but this whole thing is 90 degrees, so that is going to be 90 minus 60 degrees, which is going to be 30 degrees. So it was coming in 30 degrees from the normal and leaving at 52.6 degrees from the normal. Okay? And in order to find that, we're going to go ahead and do, well, we know that outside N1, well, actually, we don't know what N1 is on the inside, but we know it is going to be the sine of 30 degrees, and that's going to be equal to N2 on the outside, which we know what that one is going to be 1, and is leaving at the sine of 52.6 degrees. Okay, and then so N1 is just going to be equal to 1 times the sine of 52.6 divided by the sine of 30 degrees, right? And that works out to be 1.59. So this is a pretty cool problem, and that's how you do something actually complex, where you have to figure out the geometry first before you actually can figure out those angles. So typically with you, the math is actually, with students, the math is actually the easy part. It's actually figuring out what those refraction angles are, right? And it's pretty easy if you have a nice square object, right? The angle comes in, the object comes in, you get a protractor out, you measure this this incident angle over here, you measure the refracted angle here. Pretty easy to do, right? And then if you know the medium here is equal to 1, then you could figure out this one, which is basically a last problem. But you kind of get the sense that when now you get a surface that is non-traditional, not like a straight line across, well, now you have to start thinking about stuff. You have to think of where it intersects, where the incident angle, where the incident ray is intersecting the interface, and the interface is going to now be at a tangent to this circular surface. And so that if that is the interface, line, this is going to be the normal line, which is perpendicular to the interface line. Okay? So you have to start thinking of now the interface, which is now going to be a tangent. If it's a rounded surface, it's going to be, and inside the more dense medium is going to be a lower angle than the outside. Okay, and just to reiterate, when something comes in from a less dense medium to a more dense medium and is coming in along that normal, the normal line, it's still going to be slowing down. It's just not going to bend. Okay, it's going to be slowing down and speeding up. It's just not going to be bending. Okay, so let's try a couple problems. Okay. Here we go. A light ray is incidenting. It's coming in and hitting a window and refracting through. This is refracting all the way through. Which figure shows the correct path of light? Is it 1, 2, 3, or 4? Please pause the video now and try it out. Okay, you've unpaused the video now. So here we go. You have an incident ray coming in, and in number 1, when it does refract into the window, it does bend towards normal. But then something weird happens. It looks like it's almost reflecting off that imaginary normal line in this case. And it shouldn't be. It should be leaving out with the same angle to the normal that it came in on, so that this angle here should be the same angle here. So it should be doing this, but they drew this. So number 1 can't be right. Number 2 is showing it also come in, and it's also bending towards the normal, so that seems great. But then it hits the normal here, and now it's moving along the normal, which can't happen. It would have to, again, bend out, and this ray here should be parallel to this ray here. If they're both, if this is the same thing as this, okay? If the two index of refractions are the same. So this can't happen. Number 3 is just kind of all over the place. Number 3 seems to be bending in, reflecting off the normal, and then bending into the object, and then is bending out. So this seems correct, the outward portion. So this seems correct. And this angle, this angle over here seems correct, but it's this one that is incorrectly drawn. So if it bent like this, it should be bending in along the normal, bending towards that normal line. And then when it hits here, it's going to be bending back out of the normal line. So 4 seems like it's the best option. And I've drawn those here on the next line to kind of reflect what we just did. Reflect. Except I should have said refract. So, not a good joke. Anywho, back to doing this. So these are the actual answers to that last problem. So 4, again, is the answer. Okay. Let's try this again. Let's try it with, practice makes perfect, but let's do it when it might be actually refracting through multiple surfaces. In this case, there might actually be multiple answers. So go ahead and see which light rays are actually drawn correctly. Okay? And pause the video now. Okay. Let's start with number 1. When it comes from air and it hits glass and then exits through air, it's traveling along the normal the whole time. So it's not going to be bending or anything like that, even though it's going from fast to slow in glass and then speeding back up to fast again. So number 1 is drawn correctly. Number 2 shows that it's coming in along the straight line, not bending towards the normal as it should be. And then it does refract and bend away from the normal, right? So this can't happen here. It needs to be bending in along the normal, and then over here, it'll bend away from the normal. So number 2 is drawn incorrectly. Number 3, interesting problem. Okay, so it's going to be coming in, bending here, bending along the normal, and then when it gets to right here, it's bending at this angle, and then it's showing it bending towards the normal, but it should be bending either further away from the normal. So it should be either bending out or probably reflecting off the surface. That might be close to that total internal reflection angle, the critical angle, which we'll talk about in part 2 of this video. So doesn't look like 3 is drawn correctly. So that can't happen. It'll probably be reflecting back up and then refracting out and refracting out, something like this. Number 4 does seem like it's coming in along an incident ray, and it does bend towards the normal, but again, it's showing that it's reflecting off of that imaginary normal line, which can't happen. So number 4 is incorrect. Number 5 is showing a nice big angle in the beginning, and then when it slows down, it bends towards the normal. And then this angle looks like it's the same as this angle, so that's good. And then it seems to be bending away from the normal again. So, and it looks like this angle is probably the same size as this angle, this line is probably going to be parallel to this line. So that looks like it's drawn correct. Let's see what 6 is. 6 is showing it coming along the normal. Oh, and then it kind of bends away. That can't happen. It should, if it comes in along the normal, it should continue going in a straight line. Even though it's slowing down and speeding up, again, it comes in, slows down, and then speeds back up to its original speed as it was over here. It should be staying along that normal. So I'm guessing the answer should be this, 1 and 5. Let's check our answers. So we were correct. Here are the drawings, and our drawings that we kind of marked up were correct. And ooh, I actually did a good guess. It would kind of reflect off the surface, probably due to that critical angle, which we'll get to. But number 3 is a really interesting problem. So this is kind of how you reason through refraction, how light is bending towards and away from the normal, depending on if it's speeding up or slowing down. Okay? The more it slows down, the more it's going to bend towards the normal. The more it speeds back up, the more it's going to bend away from the normal, right? So you have to think about the density of those mediums. Okay? Here's some cool problems, as if the surface is rounded. So now you have to start thinking about the interface line, which is a tangent to the surface, right? And then drawing the normal line, which would be perpendicular to the interface line. Okay? All right, here, let's try it. So go ahead and pause the video now and try to see which one or ones, there could be multiple correct answers, are showing correctly drawn figures, correctly drawn light rays. Pause the video now. Okay, we're back. So here we have a light ray coming in, and it looks like it's going to be, when it hits this surface, here's going to be the surface, that's the interface. Looks like it's going to be coming in along the normal. And it's going to be slowing down, but it won't be bending. And then it'll be exiting along the normal. So the interface line is perpendicular to the normal line. So it looks like 1 should be drawn correctly. Let's try number 2. Number 2 comes in. It hits here. The interface is going to be drawn like this. It's going to be drawn at a tangent to the surface at that point. So the normal line is going to be perpendicular to that. And when it comes in, it should bend towards the normal, but it shouldn't bend that much towards the normal. So when it hits, it should come in and bend like this. So now this is the refracted ray. And now it's going to hit again. And the interface is going to be right here. And then it should be bending out away from that normal. Okay? Whatever this angle is here. So that should be the correctly drawn answer. And I should use a different color just to show our corrections. All right, so number 2 is incorrect. Let's try number 3. Number 3 is coming in. It hits the interface. It hits the interface right here, and then it draws, and it looks like it does bend towards normal. When it comes here, it shows it reflecting off the normal line, where it should be bending away from that normal. Right here. It shouldn't be reflecting off the normal. So 3 is incorrect. Number 4, it comes in, bends towards normal. That looks good. And it's continuing along there. And then it bends away from the normal. So this looks like, number 4 looks like it's correct. And they actually have those normal lines drawn correctly. Number 5 looks incorrect to me. It's not going to come in and at an incident angle and then refract along that and then bounce off. So that's just not correct. Light rays, so this is kind of showing what might be kind of like a critical angle, but the problem with a critical angle, it has to be inside. It has to be, critical angles only happen going from high dense mediums to low dense mediums. So this can't happen either. So 1 and 4 are correct. So the answer I'm thinking is the answer is 3. Let's check our answers. And it looks like we are correct. Number 1 shows an unchanged line with no green fixes, and our fixes look much like our actual fixes. And number 4 looks like it's drawn correctly. So it looks like we're right in our guesses, or informed guesses, I should say. So here's some of the weird consequences of refraction now. So when you put a ruler in water, if you notice this ruler goes in water, and if the light rays look like they're bending towards the normal, why does the ruler look like here, like it's bent away from the normal? Okay, it looks like it's actually bending up towards the surface. Well, how is that actually happening? So when you insert in the ruler into water right here, okay, what's happening is the ruler is actually bending. The ruler light rays from the tip of the ruler look like it's bending, will be bending down. Okay, so the ruler right here, which is right down here, and I should use black for this. So the ruler is actually right here. Okay, so the tip of the ruler is right here. So when it comes out, it's in the water, and it has a smaller angle here than this angle, so that this is a less dense medium than the more dense medium. Okay, and when it comes here, it's going to bend out towards our eyes, but our eyes will see the ruler along a straight line. So what we see here, this is what the sighted ruler is, but the actual ruler is way down here. So the weird thing is, when the ruler comes in, we know it's actually going in a straight line to what it was before. So the tip of the actual ruler is actually down here in the water, but it appears to be above, the sighted part of the ruler is above where the actual ruler is. So it looks like it's bending up towards the surface, which is kind of crazy. It always messes me up whenever I had to clean pools when I was younger, and on the swim team. So when I was cleaning the pool, I'd always see that bar, the pool broom, kind of bend towards the surface, and it always kind of messed me up a little bit. It startled me, and I always wondered how that actually happened. So I'm really glad I studied physics, and this kind of helped me to actually at least be okay with it now that I understand what's happening with the light rays. But still, it's kind of strange. So this happens a lot, right? Even if you're the object, if you're looking along the normal, okay, the object is going to appear above where it actually is, right? The apparent position, or the sighted position, is going to be above where it really actually is, which is down here below. And this is actually a really interesting problem, because I had a cat when I was younger, and we had fish. And one of the crazy thing is our cat was really smart, and it would hang out above the fish tank, kind of bored all day. It was an inside cat. And after a couple weeks, it actually started figuring out that the actual fishies were below where it appears to be. So when we bought goldfish, after about a couple weeks, the goldfish kind of disappeared, and then we noticed that the cat had actually figured out that refracted light ray angles, okay? And it's because our brains are perceiving along a straight line, but what's actually happening is the light rays coming out away from the goldfish and then bending away from that normal into our eyes, but our eyes see it coming in along a straight line, okay? And so it could have some really crazy consequences. For example, this fellow looks like he is, his actual body is here, but that light ray is coming out from his body and then bending away from the normal. And we are seeing light coming, so his light ray is coming out away from that normal, and the normal is going to be here, and bending away from that normal, well, we're going to think things are coming on a straight line, right? So the normal is right here, so it's bending toward, it's bending away from that normal, and we're seeing things in along a straight line. So it kind of looks like his head is disembodied from his body. His head and his arm is disembodied from his body. Well, let's practice those consequences, right? So if you wish to reach for a fish and that you see underwater, you would plunge your hand into the water directly at where you sight the fish to be, the apparent fish, above the apparent fish, or below where the apparent fish. So where is the actual fishy at? Okay. So go ahead and pause the video, take a guess as to your answer, and then actually draw how light rays are bending, okay? And try to draw this out, okay? So pause the video now. Okay. Well, we are seeing the fishy right here, okay? So we're seeing the fish right here, okay? However, here's the interface, so I'm going to draw the interface with a different color. So we're seeing the interface right here. So here's the surface. The normal line is going to be right here. And we know the light ray outside, this light ray here, this angle here has to be greater than what's inside. So the light ray coming from the fishy has to be bending away from the normal. And so what we're going to do is kind of trace this back the other direction. When it comes in, it's going to bend towards the normal. Okay, right here. So this is the refracted ray. This is refracted angle right there. And so what it looks like from the drawing, if I've got it drawn correctly, the actual fishy should be down here, and the sighted fish, or the apparent fish, is above where the actual fish is. So I'm thinking that the actual fish is below the sighted fish. Okay, and let's check our answers. And it looks like we're correct. So the light ray comes out from the fishy, it bends away from the normal into our eyes, but our eyes are interpreting it as in a straight line. Okay, pretty cool. Well, let's try it a little different circumstance. Here we have a coin. Here's where the actual coin is. Here's where the actual coin is, right here. Where would the sighted coin appear? Would it appear at the bottom of the glass, near the middle of the glass, or at the surface? So where do you think? So pause the video now and try drawing that out. Okay, you've unpaused the video. So the actual light ray is coming out, and when it comes here, it's going to bend away from the normal, right? It's going to bend away from the normal because it's air is less dense than water. But we're going to see it right here, somewhere near the middle of the glass, slightly above where it actually appears to be, since our eyes are seeing things along a straight line. Oh, that's pretty cool. Okay, let's try another problem, okay? So you're going to aim a laser beam at where a UFO appears to be, okay? So here is where so suppose you want to aim a laser beam and hit a space station antenna. Should you aim your laser beam higher, lower, or directly at where you sight the space station. So this is the sighted space station, and this is in a vacuum. Okay, so this is a vacuum, and this is air. Air is more dense, so N of air is more dense than N of a vacuum, right? So how should it work? Should light bend towards or away from the normal when it comes there? What should you do? Sorry about that. I got a little distracted by a neighborhood cat. His name's Patches. He walked by my window. Anyways, back to this. So where should you aim your laser beam in order to hit this space station? At where you sighted in, or below where you sighted in? So first of all, let's think about this for a second. Where is the actual space station? Let's make the problem a little bit more complicated, okay? Well, we know when the light rays, this is the less dense medium, it's going to come in, and in this case, we're going to be the fishy, okay? So we're kind of like the fish, and not only that, we have a curved surface. So I'm actually going to draw the normal line using green, okay? So let's try this out. I'm just going to complicate it here. So here's the normal right here. I'm thinking this is the interface. So when that light ray comes in from the space station, it should bend towards us. It should bend towards us. So it's leaving the space station, then it's going to be coming in along a straight line into our eyes. Okay. Oops, I actually made a mistake here by the drawing. Let me redo the whole thing. Great, that's fabulous. If we're sighting in the space station, we're seeing the space station right here. Okay. But where's the actual space station at? That's the question I have. So the actual space station, so here's going to be the interface. So here's where it hits. I'm going to draw the normal, just as normal as it should be. The actual space station is going to bend away from the normal here. So the actual space station should be right below where the sighted space station is. Interesting. So in a less dense medium, it actually is also below where you sight the space station. So here's where the actual space station is. So should you aim at the actual, what you think the actual space station is with the laser beam, or what the sighted space station? Well, if you're going to hit it with a beam of light, shouldn't you aim it actually at where its sighted is? That way, when the light rays from your laser is going to follow the same lines towards the actual space station, right? So if you aim it at the sighted one, directly along the sighted one, it should refract out and bend away from the normal and actually hit it. So interesting. And that's actually what they say here too. So if you're trying to hit it with a laser, you don't have to correct. You just aim at where it appears to be. Even though we know the sighted space station is, the actual space station in this drawing is right here. But the sighted space station is going to be up here. Or apparent space station, right? The fake one, the one where it appears to be, is up here. But the actual one is here. So if you shoot it with a laser beam, it's just going to follow the refracted same lines that it comes when the light from the space station follows when it comes to hit your eyes. Well, the cool thing is this has some really neat consequences, right? So if you've ever seen the sun when it's either rising or it's setting, the sun actually doesn't look like a perfect sphere. It actually looks like an oval, right? And how can the sun change shape as it's going across the sky? Right above us, when the sun is right above us at noon, it's a perfect circle, right? But when it starts to get close to the horizon, and I'm talking really close to the horizon, right when it's about to set, or right when it's about to rise, if you've noticed, it looks red, and you could actually kind of look at it, you know, and it looks red, and it's actually kind of oval. Why is that? So what do you think is the reason for that? Is it the high rate of rotation as it's coming across our sky? Is it the reflection of the sun? Is it actually reflected? It's not the actual sun. Is it the refraction that's causing this? Or is it dispersion, which I'm not sure what dispersion means. We're going to cover that the next time. So what is actually happening? So pause the video and choose your answer. Well, what's really, really neat is that the sun isn't actually where you see it. When the sun is low on the horizon, the weird thing is the sun is actually already set, or it has actually not have risen yet. So when the sun is over here, notice that here is your sight line. Here's the Earth from where you would see it. So here's the best way to see it. If you're standing right here, your horizon is right here. You wouldn't be able to see really anything below this point. So when you see the sun right here, what's actually happening is the sun is actually already set. Okay. And what happens is the sun starts to take on this slightly oval shape. So not only is that light coming in from the sun being bent, but the actual shape of the actual sun is being changed too. So that it actually starts to squish. It actually starts to squish down. So, and I drew it on the wrong thing. Sorry about that. So the sun, a light ray, is bending, and is bending towards the normal when it's coming into our atmosphere, but our eyes see it as a straight line. And so these light rays, when they're being interpreted by our brains back out, it starts to appear, that refracted sun starts to appear over here, and it's not actually here. It's actually already set, or it hasn't risen yet. So that's a really cool consequence of this. So what I want you to do is I want you to do the lab, try some of the lecture tutorials, and then try the quiz on this. Okay? All right, have a nice day.